Now we're going to look a little more closely at a covalent bond and the shapes that they make, and they have different characters based on what is bonded together for the molecule. So the first one we're going to look at here is a chemical bond's character is related to each atom's attraction for the electrons in a bond. The stronger you are, the more easily you do pull-ups. Well, just as a person has a different ability for doing a pull-up, atoms in a chemical bond have different abilities for attracting or pulling on electrons. Remember, covalent bonds are all about sharing electrons. Well, some atoms share their electrons a little more nicely than other atoms. And it also depends on what they are bonded to as to how nicely they share. So I'll start off first with electron affinity. And this just is kind of the opposite of ionization energy. And it just means that it is the tendency of an atom to accept an electron. Like I said, it is the opposite of ionization energy. If we switch to electronegativity, which we looked at in Chapter 6, okay, let's remember that that is the ability of an atom to attract an electron in a bond. So now we're talking about a bond in an atom attracting electrons versus just a single atom wherever it's at gaining an electron or losing it. We're talking about ionization energy. So now we're talking about bonding. Okay. Well, there are different types of chemical bonds based on these electronegativity differences. So if I have two things bonded together, they're often going to be different electronegativities, especially if they are different elements. So the first kind of bond we can have is going to be what's called a pure covalent bond. And these are the ones where electronegativity, or En, difference is 0. So here, in order to have a 0, we need to have the same element bonded together. Because now they are equally sharing electrons. Since they have the same electronegativity, they both want the electrons in a bond the same, so they share nicely. And that's a pure covalent. They are purely just sharing. Covalent, share. Okay? Then we have what's called a polar covalent, and that's where your electronegativity difference is between a set number, between 0.4 and 1.7. Now we don't really get into the numbers as much as just being able to identify, okay? But these are where we have unequal sharing of electrons, because we're going to have different elements bonded together. And one is going to want the electrons more than another. So you have pure covalent, polar covalent. Well, we're taking a little closer look at polar covalent and what that exactly means. Like I kind of got into before, this means it's a tug of war between two atoms. So two things are going to be bonded together and they're going to fight over who wants the electrons more. One of them always wins, because they are not of equal strength. They are not the same element. So what happens is the electrons are pulled toward one of the atoms and spend more time around that particular atom or element. And that is the one with the higher electronegativity. The electrons here are unequally shared. One of the atoms wants electrons more than the other. So this causes a partial negative charge. And then it's going to be on the more electronegative atom. I'm going to look at an example here with HCl. HCl, chlorine is much closer to fluorine than hydrogen is. So it has a higher electronegativity. It is closer to 4. Our highest value is 4. Okay? So the difference is 0.96, so it fits in there to be a polar covalent bond. Chlorine's a little bit bigger in size. Okay? But these little negatives, okay, mean that we have a partial negative. Now remember, in an ionic, I have Na plus Cl minus. Here, I have these little deltas, okay, kind of like little S's. That means this is the partial positive end, the partial negative end. So this chlorine end is a little more negative than the hydrogen end. And the further apart these two numbers are, the more the electrons sit on one side or the other. Okay? So if I have a metal and a non-metal, that's ionic. That's very, 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 very polar. Okay? It's not even classified as polar. Okay, because it's total positive, total negative. If you look at H and Cl bonded together, they are both nonmetals, so they share, but they don't share equally. Okay, chlorine is much closer to fluorine and really wants those electrons. That could be like a noble gas, so it takes those electrons. okay, and they spend more time around chlorine. Now, it doesn't mean that this electron around chlorine doesn't often go to hydrogen. It just doesn't stay there very often when they're shared. They just sit kind of closer to chlorine. Okay, now we're going to look at how the polarity goes along with an actual molecular shape, like a whole molecule, not just a particular bond, okay? And if I look at a whole molecule, if you have a lone pair, okay, or different types of atoms around the center, you're pretty much going to have a polar molecule. Okay, now they can cancel out, so you got to be careful. That's why I said pretty much, okay, because your lone pairs can cancel out, okay, if one is on top of a molecule, one is on the bottom, or the atoms can cancel if they pull in opposite directions. So let's look at some examples here. Okay, let's look at water first. Water, it has a bent shape and it is polar. Okay, it's H2O. This oxygen should actually have two lone pairs on this end. Well, lone pairs are electrons, okay, so the electrons are going to sit this direction. So we draw it with the arrow and a little positive on the end. That means the electrons move that way. So the electrons move that way. So we draw them with the arrowhead pointed towards the electrons that are going that way. Plus the oxygen is more electronegative and it is closer to fluorine than hydrogen. Remember the negative end, positive end. We draw the electrons going that direction, therefore it is polar. Now CCl4 is actually nonpolar because what happens is that the electrons are going to sit more towards chlorine on each bond, but the bonds pull equally. Okay, they're all four chlorines, so they're all pulling on those electrons equally, so they end up kind of canceling out. Now, it may not look like it because they're not going directly opposite, like one this way and one that way, but since they're all the same bond angle, it ends up that they actually all cancel. So you can cancel out polarity, okay, and have a nonpolar molecule with polar bonds if they cancel each other out. They have to be going in the exact opposite direction, which is what I was saying up here about lone pairs as well. If I have a lone pair on the top of an atom, okay, and the lone pair on the bottom, other things going on, one's going to pull this way, the other's going to pull down, and we end up with a nonpolar molecule. Okay, and we'll look more at that in a couple of worksheets. But the last example here, ammonia is polar. Okay, nitrogen is closer to fluorine. It's going to, your electrons move towards nitrogen, plus there's a lone pair on here, which is very negative, makes this end very negative, makes this end very positive for the entire ammonia molecule, and we have a polar molecule. These three polars cannot cancel out a lone pair. If you have a lone pair, that molecule is polar, unless it has one below it to cancel it out, but that's very rare. There's probably one or two structures that are like that. All right, let's take a look at the solubility of polar molecules. And solubility just is a fancy term for the ability of something to dissolve. And it's the ability of it to dissolve in any other substance. Usually we look at it as water, but just can be anything in general. While the bond type and the shape of the molecule determine its solubility. And I look a lot more at this in AP chemistry. We kind of just look at the surface of it for right now for this class. And we'll look more at how things dissolve in one another as we look at the next video, the one with intermolecular forces. Well, the phrase for this is that like dissolves like. All right, if you have a polar molecule, it'll be dissolved in something that is polar. If you have a nonpolar, it'll dissolve in nonpolar. So something nonpolar will not dissolve in something polar. The reasons we look into more in AP chemistry, not so much in here. Let's look at some questions. Okay, summarize how electronegativity difference is related to a bond character. Well, the bigger the electronegativity difference, the more polar it is. You know, the further and further and further away you get, the more polar it is until it's finally an ionic bond. Look at a polar covalent bond. That's where we have a positive, negative end to a bond. One atom wants electrons more than the other. If I look at a polar molecule, that means I have a positive and negative end to my molecule. And so now I have the electrons being pulled one way or the other overall. So this is kind of like overall versus one particular bond in a substance. You need to draw the Lewis structure and determine whether each molecule is polar or nonpolar. So the first thing I want you to do is take a minute and draw all 6 of these Lewis structures, not shapes, Lewis structures. Alright, now that we have these 5 structures, now we're going to figure out whether they're polar or nonpolar. Alright, well, in this first one, I have 4 of the same atom around my center. So each one of these is going to pull evenly out towards the fluorine. Fluorine's more electronegative. So they should cancel, except I have this lone pair here, and the lone pair is going to make this end very, very negative. That is polar. I'll go to the next one. I've got 6 things around my sulfur. They're all the same element, so that's going to actually be nonpolar. So even though these fluorines are pulling, okay, on all the electrons, they're equally doing this. So the front one cancels out with the one in the back. This one here cancels out with another one. And you end up with an overall nonpolar molecule. Look at SCl2. Okay, here now you gotta be careful. Okay, because it looks like these 2 lone pairs might cancel out because I have 2. But they actually aren't on the exact top and bottom. Remember, if you look at the shape for this, it's bent. Okay, and we've got one in the front and one behind. Well, those aren't exactly top and bottom. They're actually right next to one another. So this is actually polar, even though you've got 2 lone pairs, because they're on the same side, and there's no way they're not going to be on the same side. There's no way they get exactly 180 degrees apart. So that is polar. Look at CS2. Sulfur is more electronegative, okay? So the electrons are going to get pulled outward. They're going to get pulled outward going both directions. So this is an example of something that is nonpolar as well. Look at the last one. Okay, I've got 4 F's around the carbon. They're all the same. They're all going to equally pull. Okay, so I end up with them all canceling, which means that I have a nonpolar.